I'm going to go over how to solve exponential equations first, and then I'll show you kind of the need for logarithms and then understanding that exponential functions and logarithmic functions are inverses of each other. So we're going to use logarithms to help us solve exponential functions, or excuse me, equations that we can't do like when I want to write them using the same base. So let's do this very first example. Whenever you see an exponential equation, your first thought is to look at the bases. All right, this one is extremely straightforward because the bases are exactly the same. So if the bases are the same, then these exponents have to be equal to each other for this to be a true statement. Okay, so I'm actually going to then drop the bases and just set 2x equal to 3x plus 2. And now it becomes algebra 1. I'm going to move the 3x over to get negative x equals 2. If the opposite of x is 2, then x equals negative 2. Now, if you want, you can always check this. Plug it back in. 5 raised to the 2 times negative second power equals 5 raised to the 3 times negative 2 plus 2 power. That's going to be 5 to the negative fourth power, or 1 over 5 to the fourth power. And this is 5 raised to the negative 6 plus 2, which is negative 4. So it does work. All right. Same idea here. They all have the same base of 3. All right. I'm going to copy this one on the left. But if you look on the right, this is 3 to the 2x power over 3 to the first power. And when you guys were in Algebra 1 or even pre-algebra, you learned that one of your exponent rules said that you can subtract whenever you see that division symbol. So this would be 3 to the 2x power minus 1. So you can subtract the exponents. Now they have the same base. So let's go ahead and drop those bases and just set the exponents equal to each other. All right, moving the 2x over, you get 2x. Moving the minus 7 over with adding 7. Negative 1 plus 7 is 6, so x equals 3. All right, now here's an example of where you can't just drop the bases right away, because the base on the left side is 256 and the base on the right side is 4. But I can rewrite 256 with a base of 4. I know 4 to the first power is 4. 4 to the second power is 16. 4 cubed is 64. And 64 times 4, so 4 to the fourth power, is 256. So now I can drop those bases and set, make sure you know which 4 I'm talking about, this 4 equal to x minus 5. So 4 equals x minus 5, or x equals 9. All right, that's how you do that. Let's do one more like this with a little bit of a twist. Remember, I've been saying this now, I think this is like the third lesson in a row. When you have something that as a radical of something, you can rewrite it as 2 to the power of 1/2. All right, so the idea is now they have the same base, so I just want the exponents to be equal to each other. So 5x is equal to 1/2. Divide both sides by 5, and 1/2 divided by 5, which is the same as, let me just show some work here so I know I'm saying it. So really this is times 1/5, right? Dividing by 5 is the same as multiplying by a fifth, so you get x equals 1/10. Now this one over here, there's a couple things going on here. First thing I noticed is that it's equal to a negative. We've talked for a long time that you can plug in negative values for x, right? You can plug in -2, you can plug in -3, negative 1,000, but you'll never be able to get a negative number. You'll just get smaller numbers, right? You keep getting closer and closer to 0, but you never touch it. So 3 to the power of x plus 1 will never be a negative number. All right, so this graph over here is showing you this is the curve, the exponential growth curve of 3 raised to the power of x plus 1. All right, and you'll notice this horizontal orange line is at -2, and you'll realize since the asymptote, right, the horizontal asymptote is the x-axis, it's never going to intersect with that horizontal orange line. So that's why there's no solution, because there's no way to make this exponential function become a negative number. Okay, now let's talk about why logarithms are important. So the reason that we need logarithms is if you look at this next example, 5 raised to the x plus 2 power equals 4 to the power of x. What you'll notice is that our bases are not the same. And unfortunately, we cannot rewrite 5 and 4 using the same base like we did with that 256 base. We rewrote that using a 4. But in this case, we cannot. So when you cannot rewrite them using the same base, what you're going to do is take the log of both sides. So you can use log log, you can use the natural log, you could use your log of any base if you cared. Most students will use the log with a base of 10, the common logarithm, but you can also use the natural logarithm. ln is fine. Okay. Now, if you notice at this point, I've copied it down, but I put logs in front of both sides. And the whole point now, I told you this is kind of like the most important property from the last unit, is we can use the power property to take these powers and move them to the front. So it becomes x plus 2 times the log of 5 equals x times the log of 4. Okay, now I'm going to distribute the left side. So x times the log of 5 plus 2 times the log of 5 equals x times the log of 4. Let's go ahead and get our x's to one side. So you'll notice I'm going to copy down x times the log of 5 minus x times the log of 4. So I moved it over. Move over this 2 to be negative 2 times the log of 5. All right, factor out the x's. You get the log of 5 minus the log of 4. Copy the right side. And then we're going to divide both sides by that log of 5 minus log of 4. So the answer is this. Now, this is a lot. I recognize that your answer has 3 separate logarithms in the answer. So go ahead and just leave it like that. I'll show you in class where I'll do one of these in class and we'll check it with Desmos so you can see that I'm not asking you to approximate this. If you feel the need to type that into a calculator to approximate it, feel free, but it is not necessary. You can just leave it as that fraction with logs. Let's try this next one. Same thing. I see a base of 2. I see a base of 3. Unfortunately, I cannot rewrite those as one base. So I'm going to take the log on both sides. And just to mix it up, I'm going to use the natural log. Again, you can use the common log if you want. I always prefer the natural log once I learned it. Same property applies. Move those variables, the variables and this case has x plus 1. Move it to the front. All right. I'm going to distribute the one on the right to be x times the natural log of 3 plus the natural log of 3. Remember to get everything that has the variable x to one side and everything that doesn't to the other. Okay, factor out the x's. And then we're going to divide. So x equals the natural log of 3 over the natural log of 2 minus the natural log of 3. And that's it. Like I said, if you want to find the approximate answer, go ahead, but you don't need to. Okay, so that's kind of the necessity or the need for logarithms, is trying to solve these exponential equations when you're unable to rewrite their bases to be the same base. Okay, let's solve some of these containing e. All right, now I told you up here, right, you have the option to use the logarithm, the natural logarithm, any log you want. When you're solving and you've got e involved, you're going to want to use the natural log. All right, that's kind of your dead giveaway to use the natural log. The first thing you want to do is you want to isolate for that e. So I'm going to first divide both sides by 20. All right, so I'm going to get 5 equals e raised to the 2t power. Now, as I said, at this point, we're trying to solve for t, right, which is in the exponent. So to kind of move it to the front, we're going to need that logarithm. And as I mentioned, go ahead and use the natural logarithm when you have that base of e. Okay? So I'm going to now move with the power property, move that 2t to the front to get 2t times the natural log of e. And now this is a really important thing to know that's going to help you when you're solving equations with e. The natural log of e is just equal to 1. All right, the reason is because there's a base e there, and e to the first power is e. All right, so just go ahead and commit this to memory. The natural log of e is 1. Having this knowledge is going to help you when you're solving these equations containing the letter e. So really, when I have 2t times the natural log of e, I'll rewrite it for this step, but it's just gone because 1 times 2t is t. So to get the answer, I'm going to move that 2 over with division to write it as the natural log of 5 divided by 2. Again, you can get an approximation in decimals. There's no reason to. Just leave it as the fraction. All right, let's solve this one. Let's move over that 5 first, right? We're solving for e, or isolating for e. Let me rephrase. We're solving for x, but we're isolating for e first. Then that will allow us to find x. So let's see, 12 minus 5 is 7. Divide the 4 over, and you get e to the 2x power equals 7/4. Remember to take the natural log once you've isolated that e, or do it to both sides. Power property says we can move it in front. And as I mentioned earlier, the natural log of e is just 1. So this is just 2x equals the natural log of 7/4. And to finish it, it's going to be the natural log of 7/4 divided by 2. Okay, let's try this one. Now, this one's a little tricky. You've got 2 instances of e. So let's go ahead and move the 7e to the 2t power over here and move the 3 to the other side, which is a negative. All right, and then I'm going to subtract. This is 1e to the 2t power minus 7e to the 2t power, which is negative 6e raised to the power of 2t. Let's move the negative 6 over with division. And negative 3 divided by negative 6 is 1/2. And now I'm ready to take the natural log of both sides. Let's see if you're good with this step that I'm going to do. Oh, don't forget the natural log over here. All right, when I move that 2t to the front, it's going to multiply by the natural log of e, which is just 1. So I'm just going to go ahead and drop that now. And if you were to finish this, it's the natural log of 1/2 divided by 2. All right, so that's how it looks when you're solving some of these equations that contain that e. Now, the next thing, extraneous solutions. We've talked about extraneous solutions. This is where you're doing your work, and then all of a sudden you get a solution that ends up, when you plug it back into the original equation, it does not make a true statement. So you always want to check your answers just to make sure, and this is something that will come up with logarithms from time to time, where when you're solving these equations, you might get a potential extraneous solution. So these next two are going to kind of blow your mind the first time you see them. This is e raised to the power of 2x minus e raised to the power of x equals 56. So these are equations involving e, all right? But what's going to be kind of new to you, and don't be mad, right? This is something that's going to happen from time to time, is I'm going to move this 56 over and make it minus 56. And now I know it's hard to believe, but I'm actually going to factor this. If you want to think of this as like x squared minus x minus 56, but in essence, it's not, right? It's e to the power of x is going to go here, but we need factors of negative 56 that add to negative 1. That's going to be negative 8 and positive 7. Right? And you might be wondering, well, how did you know how to do that? Well, if I were to distribute this, and I'll write this down, but do not feel like you ever need to do this, right? If I were to multiply this out, the very first thing you multiply is e to the x times e to the x, right? So this times this. And if you remember your work in pre-algebra, right, when you're multiplying things that have the same base, it's e raised to the x plus x power, right? You add the exponents, and x plus x gives you that 2x. So that's why when I see problems like this, I know that I'm going to end up factoring. All right, so let's set each equal to 0. So e to the power of x minus 8 equals 0. E to the power of x plus 7 equals 0. Move them over, and you get equals 8. This one you get equals negative 7. Now, I know I mentioned this before. I'll mention it again. Whenever you have an exponential equation or function, whatever the base is, right? If your base is between 0 and 1, or if your base is greater than 1, E is greater than 1. It's approximately 2.7183. It will never be a negative, right? This right here will never be true. There's no way to make this a true statement. Okay, so this kind of side here to the right would give us an extraneous solution. So I just stop working on the right side and I focus on the left. Take the natural log of both sides, right? And as I said before, right, the x is going to move to the front, right? And it's going to multiply by that natural log of e, which you know is just 1. So x equals the natural log of 8. So this is the only one that actually ends up working for this first example. Let's do another one very similar. Get everything to one side. So minus e to the x minus 2 equals 0. We're going to factor it just like we did before. So e to the power of x. I need factors of negative 2 that add to negative 1, which is going to be negative 2 and plus 1. Set them equal to 0. All right, move the constants over, and you'll notice immediately this one on the right is going to give us an extraneous solution because there's no way that we could ever make an x value that when it's the exponent of the base e would ever give you a negative. So this would end up being extraneous. All right, so I focus on this one. The natural log of e to the power of x equals the natural log of 2, so x equals the natural log of 2. All right, now let's move into the last thing and then we'll be done. When you solve equations that already contain the log, so far, every single equation we've done so far did not have any logarithms, right? We had to use them sometimes, right? At the beginning, we did not when I was able to rewrite the bases using the same number, all right? But we ended up using logarithms to help us find the solutions for exponential equations. These are different. These are called logarithmic equations. They already have logs in them. So there's really two things I'm trying to do. I'm either trying to get one log on one side or one log on both sides. If I can do this, one of these two things, so this one, either or, then I can have success in solving these logarithmic equations. So I see one log here. Let's get everything that's not a log to the other side. 10 minus 6 is 4. All right, and if you remember, the base in your natural log is e. So if I were to swoop at this point, once I get one log on one side, I'm going to swoop. E to the fourth power gives you x. So e to the fourth power gives you x. Guys, this is the answer, right? If you want to tell me what e to the fourth power is, go for it, right? But there's no reason to. E to the fourth power is x. Let's try this one, all right? You'll notice this is 2 times the natural log of x plus 1. Let's divide both sides by 2. So now I have the natural log of x plus 1 equals 5. This is one log on one side, just like I did before. On the previous one, this is the base of e. So it's e to the fifth power gives you x plus 1. E to the fifth power equals x plus 1. Let's solve for x by subtracting 1. And you get e to the fifth power minus 1. So this is our answer. Okay, these last two. All right, these last two already have one log on both sides, but if it didn't, you might need to use some properties to get this one to be true, where it's one log on both sides. So if you have one log on both sides and they're the same, right? In this case, they're both the natural log, then this argument and this argument are actually going to be the same thing. So x squared equals 2x plus 3. I got to find the x values that make this true. This is now a quadratic equation. Let's move everything to one side. Set it equal to 0 so we can factor. I know it seems unfair sometimes that these logarithmic problems really just become quadratic equations again. So as I said, factoring will never leave you alone. So factors of negative 3 that add to negative 2, that's minus 3 and plus 1. So if I set them equal to 0, I get 3 and I get negative 1. Now, don't forget, as I told you earlier in this lesson, you could encounter some extraneous solutions. So make sure you check these by plugging them in. You have the natural log of 3 squared equals the natural log of 2 times 3 plus 3. Let's see if that works. So the natural log of 9 equals the natural log of 2 times 3 is 6. 6 plus 3 is 9. That checks out. So this one is good. Let's try negative 1. The natural log of negative 1 squared equals the natural log of 2 times negative 1 plus 3. Negative 1 squared is going to be 1. And this one is going to be the natural log of 2 times negative 1 is negative 2 plus 3 is 1. That also works. They both end up working. Don't forget to check them. Okay. This last one here, all right, again, they have the same base, right, of e. So I can set the arguments equal to each other. X squared equals 1. All right. So this is going to be x squared equals 1. All right. To get x by itself, I'm going to take the square root of both sides. Since I'm doing the square root, I need to write plus or minus 1. So make sure you plug these both in, and negative 1 squared is 1, 1 squared is 1, so they both end up working. All right, there's another way to solve this if you wanted to. The natural log of 1 is 0. All right, so if you wanted to set this up to be the natural log of x squared equals 0, and then you would swoop to be e to the 0 power equals x squared. Well, e to the 0 power is 1, so it ends up giving you the same, work. You keep going. Okay, that's it, guys. Make sure you try the links here on solving these exponential and logarithmic equations. Good luck.